So hey guys, welcome back. This is day 2 of gravitation. In yesterday's class, I just gave an introduction to the whole idea of gravitation and how do we write the forces. And there are some properties that I've discussed about the force, like how they're called as central forces and the conservative forces, and then what? I even gave you a form of like how do you put it in a vector form and all, and then some gravitational facts. That's all right. Like I forgot to tell you that you might have all watched the video of the gravity that I made on Gravity movie. That is quite informative. I suggest you watch it again right after this topic because you'll get a lot more doubts out of this. Okay. Now, in today's class, we'll just do a lot of problems on the basic gravitation and I'll just introduce you to a new small topic. All right. Let me just start with a simple question. I want a quick answer. We all know F is G m1 m2 by r square, and yeah, it is defined for only particle masses, but it is coincidentally working for spherical masses, and we can mathematically prove it. And then yeah, it was pretty much that we discussed. So let's just talk about a single simple problem. I have a mass m, I have a mass 2m. What's the force in between them if the distance between them is given as r? So g 2m m by r square. And you all remember the force direction must be towards each other, towards the centers, that is for sure. Now, using this idea, I'm going to give you some problems and I want you to find the forces. Okay, there is mass m here, 2m and 3m. The distance is a and the distance is a. Find the net force acting on the mass which is its origin. Find the net force acting on that mass. How do you write it? Like you can raise your hand and already give the answer right away. Guys, you can raise your hands and just give the answers right away. You don't really have to do all the math. Yeah.
Sir,
How
G phi m square
So
by
pi
a
g
square.
m square upon a square.
Now it's always better to simply represent them in terms of vectors because we have more information. We can finally give the resultant values, but it's always good to give them in vectors. So there are two forces acting on it, one towards this, the other towards this. So the forces are G 3m m by a square. Since it is in this direction, I write it as I cap. The other force is G m 2m by a square. The other force is given as j cap.
J cap, sir.
Okay, so you can finally like write these two in the same term and find the resultant and all, but it's always suggested that you keep them in the vector form itself, like this, just like this, m2m by a square j cap. It's always good to have them like this so that there is more information. Okay,
Okay, sir.
I'll give you another question. Try to answer this. Anybody? All the distances are a only. What do you do this time? There are three forces acting on the origin. I mean, the mass at the origin. Sharad, how would you put it?
Sir, here the in the vertical axis, sir, there's 3m and m, sir, in the opposite direction. So we'll
Yeah.
have to subtract one from the other.
So I'm going to write the answer directly. Okay. G 2m m by a square for this mass because of this mass. I cap
Cap plus j cap.
plus G 3m m by a square plus j cap plus G m m by a square minus j cap. Can we write it like this? We can just leave it like this, but sometimes they give you they ask you a simplified answer. If you can leave it like this, there is all information. Like you are clearly indicating all where the masses are. Like you're clearly talking about the whole problem in an equation. Okay, it's totally fine if you leave it like that. You can give the final what do you say, the simplified answer also all the time. Okay, the problems get a little complicated when you see things like this. So there is four masses, m, 2m, 3m, 4m. on the squarish plate, means not a plate, on a squarish space. So I want the force acting on the horizon. How would you write this now? Everyone can write these two, I'm pretty sure. When you're writing this, you need to be really careful. Can somebody give me an idea how would you write it?
Sir, I'll take
The
components.
better take a shorter distance from M to 3M, sir. And
Mhm.
that should be root 2A, sir.
Okay.
Sir, take components.
And we just do the normal thing,
Let me
sir.
let me write it. G 4m into m by a square I cap. Everyone agrees with this.
Yes,
This is
sir.
done. G 2m m by a square j cap. Everyone agrees with this also. But when it comes to this part is also done. When it comes to the third mass, when you write G 3m m by root 2a whole square, this is all good. Root 2a whole square is also fine, but you need to mention the direction also. How would you mention the direction? Anybody?
Excuse me, sir. Can I say, sir?
Yeah.
Sir, we'll not take it that way. We can just take the components along I and j, right? Sir?
Components of mass.
Components of that thing. Yes, sir.
Components of mass. You take the components of mass. Of course, who am I kidding? This is Aniket from a different universe, right? How would you write the direction?
Sir,
We'll take the components of the displacement,
Root
sir.
2a kept, sir.
But I'm sure you all are you not
Sir, can
aware
we
that
say
the unit vector in this direction? What is the unit vector in this direction? Are you
Displacement.
I cap plus j cap by root 2? Oh, you all forgot that.
Sir, we remember that, sir. That's what I said.
Yeah. You can simply write it as like you simply point out the unit vector that is going in that direction, I cap plus j cap by root 2, and that's it. So this is how you represent the force acting on this mass. Yeah, you can definitely simplify it if someone's asking you. That's not my bit. You can do the calculator, you can do the math. I'm not doing it. Okay. Now, the problems are not that this simple all the time. Okay. The problems get a little more complicated when they give masses on the same lines. M, 2m, 3m. Okay. The distance is a by 2. What is the force acting on this mass? What is the force acting on the smaller mass? How would you write this? I guess you can write it, right? The first force and the second force both are acting in the same direction. So all you need to do is, first of all, take these two, G 3m into m by a square, and then take these three, G 2m m by a by 2 whole square. Since they're in the same direction, I'm not I'm not putting any vectors there. But this is not the interesting part. The part where it gets interesting is this. They give you masses like 5m, 4m, and ask you have to put some m, and what the distance in between them is d. They give it that. They give you the value. At what point can I put this m so that the force acting on it is 0? Because both the forces, both attracting forces are coming from both the directions. Force acting on that is 0. How do you do it?
Sir, you
Sir,
have
on
given
the
us the
center
whole
of mass we
distance
can
D.
put, I think.
What?
On the center of mass of all three, we can put m. Yes, sir. Then the force will be balanced.
Are you sure about it?
I'm guessing, sir.
No. I'm pretty sure that it won't work because in center of masses, you only have x1, x2, x3. But when you're writing forces, you have r square, r square. So I'm like intuitively can tell that that's not going to work.
Sir, I have one method, sir.
Yeah, tell me.
Sir, the whole distance D. So I'll take any one distance as x and others D minus x.
Beautiful.
Then, sir, what I will do is let's calculate the force on M by using this, sir. By using these two distances, we will calculate the force.
Are you
Now
talking
we know
about
that the
this?
sum will be 0. And just equate it, we get the answer.
Are you agreeing with what I just wrote on the screen right now?
Yes, sir.
Yeah. So when I equate these two, everything gets cancelled, and all I need to do is simply find the value of x. That's all.
Sir, I have another approach, sir.
Yeah. Tell me.
So like on the left side we have 5m and on the right side we have 4m, sir.
Okay.
So we can say, sir, we can say that m lies like m m internally divides this line joining 5m and 4m in the ratios of 16 is to 25, sir.
That is correct.
Are you sure?
Yes, sir.
Okay, like let me first of all tell you some point, and then we come back to this the thing that you're talking about. If you
Sorry for
observe,
the
you'll get the
summary.
x value in terms of d, not d by 2, in terms of d. Okay, but the interesting fact here is it does not depend on what the mass that you put there in the middle. So the interesting fact that you need to catch here is whenever you decide these masses 5m and 4m, whenever you fix it on these masses, it and whenever you find that specific point at which the force is acting as zero, like let's call this as a point, you can call this as a, what do you call it, as 0 point,
Internal bisector.
what, there's a word for this point. Okay, why don't we just look in the problems? It is given as the word is given. Let me find out. I mean, I can't remember the word. It's a simple word. Why can't I just null point? Yeah, I got it without looking at it. Yeah, this point is called as the null point. The thing is, no matter what mass do you put there at the null point, the force acting on it is always zero. It doesn't matter what masses you put in. Okay, so the distances only depend on 5m and 5m. I mean, like kind of masses that you have here, like the kind of masses that you put there, they decide where the point is. That's why it doesn't really matter what the mass that you put there in the null point. So they might give you some problems like they sometimes give you 16m and 9m and ask you where the null point is. They talk about where the null point is. So you people get just keep this in mind. Okay, like the null point, to find the null point, all you need to do is write x, take any random mass, take m, take m1, take m2, like take any random mass, put it there, try to write the forces between on it from in both the directions, try to find the null point. And it doesn't really matter that m, it will get cancelled easily, like here, like, even though I had some mass as mx or mz or whatever it is, the mass immediately gets cancelled. You don't even have to care about that specific mass. Okay, so that, remember the idea about null points. So null points are always important. You
Sir, is
can
my
have null,
shortcut correct,
yeah,
sir? Sir, my shortcut, sir, the shortcut method which I said, like
yeah, the
that
shortcut,
point.
not a shortcut method, is just an intuitive method. Okay, like just say I have 16m and 9m, and the null point is somewhere around here, so I write it as x and d minus x. So I put some mz mass, randomly mz. Okay, I write the forces as 16m into mz by x square, g 9m into mz by d minus x square. G gets cancelled, mz gets cancelled, mm gets cancelled. What you have here is 16 by 9 equals to x by d minus x whole square. So what I can say is, from this, 4 by 3 equals to x by d minus x. So from this thing, you can clearly give the value of x and d minus x. What you're trying to say is x comma d minus x, or you can simply say when you have 16m and 9m, this space must be divided in the ratio of 4:3. Is that what you're trying to say, Sharath? If you divide this space into
Sir,
4,
it should be 3:4, sir.
what?
It should be 3:4, right, sir?
No. It is 4:3 only. You should be going away from this mass. Like this is a heavy mass, right?
Yes, sir. Yes, sir. Got it, sir. Correct.
So it is 4:3 only. So in the ratio of 4:3, you will find the null point. Okay, it is not the center of mass. Remember, Aniket, I don't know where you came up with this idea. Maybe in your parallel universe where you come from, it is a possibility, but in our universe, this is how it works. Okay, 4:3. So it's like square root of these things will give you the amount of ratio where it should be divided, the null point. Okay. So that is one more thing, the idea of null point. And they give you more questions like this. Okay, so two masses, one big mass, one small mass, or big mass is fixed. The small mass is going in a circular motion around it, just using gravitational force. So what is the relation between V and all? We all can easily do it, I guess. The force is nothing, oh, I'm sorry. Gravitational force is nothing but Gmm by r square, if the radius is r. How do you approach it? Gmm by r square is nothing but, guys, very easy, right? Mv square by r. And m cancels, you get some values like gm by r equals to v square and all. We will come back to this problem, but this is just a mathematical problem that I gave you, like where one mass is fixed, the other mass is going around in circular motion around it just because of gravitational force. No, this is not just the case, there are more problems. Okay, they give you a problem where two masses, two equal masses m and m, two equal masses m and m going around in circular motion. It's like both are going around circular motion because of the force of attraction in between them, because of the same force of attraction in between them. Exactly, Sharat says twin stars. I was going to mention this. You all know the fact about the twin stars, so the twin star solar system. Where do you see that in movies? Has any of you watched the movie Star Wars? In the movie, there's iconic shot where the hero stands right next to a twin star sunset. Like there are, it's not a strange fact. Okay, if we have a twin star system, we'll simply look at two suns. That's all. There is nothing strange and nothing different in a twin star system. It's just that both the twin stars are actually like heavy masses going around each other, and all the planets are around the orbit around them. That's all. Okay, it's the same thing. We see that in our movie. Okay, but like we don't get things that complicated. It's very simple, like this problem. Since the radius of the orbit is r, the distance in between them is 2r. So what I can say is g m by 2r whole square is a force of attraction between them, equals to mv square by r. Again, they ask you the relation between v and all. You can simply say Alpha Centauri is a triple star system. Maybe I haven't heard about it. I'll Google it. Thanks Aditya for the information. I hope this is clear, guys. Like all I did is like force acting on this is the force I wrote, and that equals to mv square by r. It's a simple problem again. Okay, and the problems get a lot more complicated now. This is not just it. Okay, Aditya, what is it?
Sir, in the previous two problems, can they ask us like what will be the minimum velocity to continue that
There is
trajectory?
no minimum velocity. There should be a specific velocity.
Like the required velocity.
No, yeah, there should be a specific velocity so that it goes in the same orbit. If the velocity changes, the orbits change, everything
Yes.
changes. Okay.
So can they ask this kind of question to us?
There is a chance, yeah.
Okay, sir.
And the problems get complicated like this sometimes. Okay, so they give a 3-body system. All of them are going in circular motion. M of a triangle side A, they are going in a circular motion. Now guys, clearly observe two forces acting on the body, which are nothing but g mm by a square in this direction, again g mm by a square in this direction. The resultant of these two forces, by making a 60-degree angle, you can all find this resultant force. What's the resultant when you have two forces at 60 degrees? F and F at 60 degrees. Does anyone remember the vectors? Root over F1 square plus F2 square. I think it's root 3F, if I'm not wrong. Cos 60. Yeah, it is root 3F only. Aditya, if that's your answer, bring your hand on. Okay, so the root 3F value. So in this problem, since the bodies are going in a circular motion, and they have a force of root 3 gmm by a square, which is equals to mv square by r. Now here the radius is difficult again, like it's a different value. This is the radius value. Can somebody give me the value of a radius when you have a triangle, equilateral triangle of side A? What is this distance? A by anybody? I don't remember the value. Is it A by root 3? Yeah, the circumcenter. The radius of the circumcenter. Okay. Anybody remembers the value? If you don't, you're going to die. It's not going to change anything for me. Anyway, like whatever the value that you get, that is the radius. You put it here and you solve the entire problem. Okay. So that is one more idea, and the problems don't stop there also. Okay, they give you a 4 mass system sometimes like this. They go in a circular motion. So this time you need to be a lot more careful. Write 1, 2, 3, all the 3 forces. Write the resultant. You finally find the resultant in this direction, which is towards the center, and you equate it to mv square by r, and you solve the problem. I think this is the problem that is given in HC Verma. You put some effort to and try to find the answer for that problem. All right. So this also checks. I think I've discussed too many problems on gravitational forces already. Are there more models? There is this, there is that, and yeah, I think it's it. I think we can. I mean, I'm going to stop at this point to try to find the resultant forces. We'll go further and solve more questions later once we get into practice. Aniket. Aniket. Mr. Aniket, I can't hear you. Did you go to Mars?
Can you hear me now?
Yeah, I can hear you now.
Yes, sir. So in this whole thing, the only problem is of finding resultant, right, sir?
Yeah, the whole problem is about finding the resultant and also writing the radius. You must be careful about, some people simply take this as a radius. They commit a mistake doing that. Okay, so you need be careful about finding the radius also. All right. Now, let's talk about potential energy. Now, why did potential energy again come here? Because, like, if you remember the idea that potential energy, we define potential energy whenever there is a system which is not stable, like whenever there is a block, let us say, simply resting on a surface, calm, doing nothing, quite literally nothing. There's nothing to talk about this block. It doesn't have any kinetic energy, or it's not moving. We can't really do anything. We don't really have to say anything about it. But when that block is attached to a spring and is pressed against and released, the block is not anymore at rest. It's not just being at rest. It's not it's not a stable system anymore. It is losing energy, it is gaining energy, and there's a lot of things happening. Okay, and when you leave a block from a height, if you leave a block from a height and it stays there, there's nothing to talk about the block, but it clearly comes down. So I need to explain the instability of a system in some way or the other, and that is why we came up with the idea of potential energy. We simply did something we wrote the work done by some force which is taking there, like who took it there in the first place. Okay, we found the work done by some forces and said that those works done is actually stored in the form of potential energy. So it has some potential energy of mgh. Similarly, it has some potential energy of half kx square. We've all talked about it. Now we are going to talk about the same kind of potential energy in this also, like, because whenever I leave two masses 3m 2m just like this on a surface or in space, if I'm just leaving them there, if they're totally calm, they're not doing anything, we didn't really have to talk about anything about them. But they tend to attract each other. The system is not being stable, it is coming towards each other. Okay, the system is not stable anymore. So in these cases, when the system is not stable, I need to talk about the potential energy. Now, guys, I'm going to do some derivation. Do you want the derivation? I mean, you won't remember it anyway. Even if I tell you that how to derive it, a lot of people just end up doing it wrong, or you don't even do it anywhere. So let me do it anyway. Like, let me take two masses, M1, M2, at a distance R. I want to define the potential energy of this system. So what I need to do is, I need to find the work done in bringing the system here, like forming the system. As if I imagine that M1 is already there. M1 is already there. We can imagine different ways. Okay, we can imagine both the masses are brought here. We can imagine both the masses are brought here. That is a complicated way to do it. I can imagine one mass is already here, the other mass is brought it here. The second mass is here, the first mass is brought in here. I can imagine anywhere because it's just a frame of reference. It doesn't really matter. Aniket, what is it?
So can we just say like both masses were together but they were pulled apart?
What?
Both masses were like next to each other, sticking to each other. Then they were pulled apart. So the potential energy that way can
Well,
be.
yeah, we can say that. We can definitely say that. But when they're together, how close were they? What's the distance between them when they're together?
Why does that matter, sir?
No, tell me. Like you have to define a starting position, right? So how
Okay.
close were they?
Like 0, sir.
How can two bodies be at 0 distance? Which means you're talking about the same point.
Yes, sir.
You get my point? Two masses
Yes, sir.
completely the same. It doesn't exist. It doesn't work that way. You get it?
Yes, sir.
So no, that is why we don't start from this point. There is another way to do it. I start from the other end, which is infinity. When the other mass M2, I'm drawing it here as infinity. They don't consider it as infinity. I cannot draw it out of my iPad and say it as infinity. When is it infinity? The distance infinity, there is no effect at all. There is no force in between them at all. So when I have to move it here, I don't really have to put any force. But as I'm bringing it to a distance, let's call them as like I have to bring it to a distance d. But when it is here, it is already being attracted by some force, some gravitational force. It is already being attracted by a gravitational force. I want the body to come there and stop. I want some stability. What should I do? When it is coming, when the body is coming, I should constantly apply some external force. It is as if you and your friend or your girlfriend meeting after a long time, you being attracted to each other, but your parents are trying to stop. That's a very bad example. I'm sorry, but yeah, let's just come back to this thing. The masses are being attracted towards each other very strongly, like not very strongly attracted, but I'm trying to stop it so that the masses come and stop at a point called D. I want them to stop at a point D. So this external force is very necessary. The external force that I'm talking about is very necessary to bring the mass slowly to the point and stop it there. So whatever the work done that is done by the external force, the work done by that external force will store as a potential energy in this system. Clearly observe one point. The mass was going in this direction. External force was always in this direction. It was always trying to stop. It was always trying to stop. So the work done is definitely a negative value, and that will reflect here. The potential energy also will come as a negative value. You try to observe that point. We will do the mathematics of it later, right now maybe, but the potential energy stored in the system will also be a negative value mathematically. Does it really have a physical significance? Strictly speaking, no, it doesn't really have any physical significance that we have a negative potential energy. It's just we clearly is looking at the situation as if the external force has done some negative work. So that is why the potential energy is seen as a negative value. Now, let us find out how much it is. Okay, let us find out how much it is. It's not writing. My pen is not writing. Why? Why aren't you writing? What has happened to you? What did I do to you? Yeah, it's working. So M1, M2 starts at infinity, which is here, and comes to point D. So M2 travels all the way here. During the travel, I need to find out the work done by the external force, but the external force is not constant. Do you observe? Because the gravitational force here was 0. Here it has some force. So that gravitation force is changing. So external force also has to change. So that is why I'm taking some random point somewhere in here, which is at a distance r. In that random point, during a displacement of dr, in that random point during a displacement of dr, I will try to write the work done. I hope you're getting my point. Now at this situation, the gravitational force F is g m1 m2 by r square. So the external force to stop it must be the same value. So F external is g m1 m2 by r square only, but it's in the opposite direction. We will mention all the directions later. Now when I write the work done dw, all I have to do is integral F external dr. I do all the math g m1 m2. Guys, I'm not going to complete into a complete detailed version because a lot of people get confused here with the directions. There are multiple positive signs and negative signs constantly change, or not constantly change. Like there are 3 steps where it converts into a positive sign and the negative sign, and then a positive and the negative. And the end, you will end up with an answer saying g m1 m2 by r with a negative sign. Okay, this is just gonna confuse you. Even in HCV, it was confusing. Even in HCV, he didn't mention it properly. I can clearly say that. Okay, I mean, he will give the final answer clearly, but even in HCV, it was quite confusing to a lot of people. Let's not disturb that thought. It is, in fact, it was given different in your NCERT textbook in HCV. It was completely different, not completely with the science and all. But the idea that you need to understand is what we did is we simply took this force, work done by that external force is stored as a potential energy, and the potential energy in between those two masses is actually I put the limits and it comes as a D. The thing that you need to remember in the end is whenever I put two masses, M1, M2 at a distance D, the potential energy in between them is minus Gm1 M2 by D. That's it. That is the thing that you need to observe, remember. Okay, Aniket.
So one small doubt.
Yeah.
Then for gravitational potential energy, why don't we have this thing?
What?
We have MGH formula, right, sir?
Now we will. This is actually MGH only. It will convert into MGH slowly. You'll see that.
Sir.
Oh, by the end of this topic, you'll be able to convert this thing into MGH. Like this actually gets converted into MGH easily. Like it's not a big deal. Okay. So this is a potential energy, guys. This is how you write the gravitational potential energy. Yeah, we used to write gravitational potential energy as mgh, but that is when we were kids. We didn't really have anything like any other way to write it. But this is a proper way. This is a gravitational potential energy to be written in a proper way. So whenever you have two masses, m to m, distance separated by distance r, so the potential energy is immediately minus g m2m by r. Guys, remember you're writing r, not r square. Okay, some people get confused with the formula. So this is the potential energy. Now what if you have multiple masses like this? What is the potential energy now? All you need to do is write all the three combinations. That's all. If you have four masses, write all the combinations. In four masses, you will have let us say m1, m2, m3, m4. Here I'm writing m1, m2, m3. So here you'll only have three combinations: m1, m2, m2, m3, m3, m1. You don't have any other new combination here. But in this thing, you have 1, 2, 3, 4, and 5, 6. So you'll have to write 6 terms here. Here you'll only have to write 3 terms. Join, like gravitational potential energy is a scalar quantity. So all you need to do is simply add all that. So minus g m1 m2 by r, minus g m2 m3 by r, minus g m3 m1 by r. Simply add that all and you'll get the value. Aniket has a doubt. Aniket, what is it?
Small dot. This potential energy, in which mass is it stored, sir? Exactly.
In which mass?
It's stored, sir. Like for a block and Earth, we were saying it was stored in the block.
No, in between them. In between them. It doesn't store, like if you remember this point, it doesn't store in this mass or in this mass. It stores in between them. In the field, in that space, it's stored.
Okay, sir. Because in our material, it was like few lines are written. It is stored in the block and then it converts to kinetic energy.
What? No, that is a spring block system. In a spring block system, it is stored in spring, then it goes to block and then stores in spring and then block. Here in this problem, no, it's a gravitational potential energy. It doesn't store in a mass or it doesn't store in a spring. It stores in the space itself.
Okay, sir.
Okay. Yeah. So yeah, Aditya is asking, is that gravitational field? In a way, yes. Aditya, in a way, you can say that is nothing but gravitational field energy. We will talk about it maybe in second year. We will talk about how the field is nothing but energy. People interpret field as energy. Okay, that's a whole different story. But you don't really need to do PhDs right now. All you need to do is simple problems like 3m mass, 2m mass, they are released at a distance d. This is fixed. So only 2m mass moves. By the time 2m comes here, what is the velocity when they are at a distance d by 2? Can somebody tell me? Can somebody tell me? It is the one mass is fixed, the other mass is here. It's released, it is coming towards this. By the time the cover they are at a distance d by 2, what is the velocity? How do you do it?
Sir, initial potential energy minus this potential energy.
Is the kinetic energy. Like, let me clearly do it for everyone. Okay. Initially, the system is here. I'm just drawing smaller diagrams. Okay. At a distance d, masses were what? 3m and 2m. They are at rest. Finally, they are here at a distance d by 2, and also it has some velocity. So initially all it has is only potential energy, which is minus g 3m 2m by d. This is the initial potential energy. It is the initial total energy. There is no kinetic energy. So I'm just writing 0. There is no kinetic energy initially. Now in this case, minus g 3m 2m by d by 2 plus half mv square also. Half 2m into v square, because the mass is 2m. All you need to do is equate this into this to this. This is the total initial energy. This is the total final energy. I equate these two and find the velocity. Anyone has any doubt in this problem? It's quite easy, I guess. There is nothing to get confused or anything like that. Nope. So there are problems like this in HC Verma also. You try to put some efforts. Just before you leaving, one more question, where both the masses are free. 3m 2m released from a distance d. Both the masses moved. Both the masses moved to a new position. So both have velocities v1, v2. How will you solve this question? How do you relate v1 and v2? Anybody? Can somebody relate v1 and v2? Anybody else?
So maybe we can just solve like that one mass is not moving only and relatively the other mass is moving with this velocity.
I'm asking you to relate v1 and v2. Yeah, you can definitely write potential energy, initial total energy equals to total final energy, but those equations are not enough because you have two variables here. It's a simple thing. You are all just blind to see, which is there is no external force on the system. So (3m into v1 equals to 2m into v2. What is this? conservation of momentum. So you use this and you use the energy conservation to find the velocities. I will discuss these problems tomorrow. All I wanted to discuss is up to this point only, like how to write the potential energy today. Okay, the problems after this discussed after the potential energy idea, we will do that. We will do those problems on Monday most probably. Okay, guys, tell me what is it?
So in the previous one, we cannot do this conservation of momentum where one mass was fixed.
But you don't need to in the first place. You cannot and you don't need to because it is fixed. The first mass is fixed, right? How is it fixed? Someone's holding on to it, which means someone's actually applying some force onto it. So that is why you cannot do it. Get it? Aditya.
Sir, in the very last problem what you have given,
Uh-huh.
like this type of problem we have came across during collision also, while we had such big equation. If we see, if I want to solve it, it will become a tremendous equation, sir.
It will actually, yeah.
So like in collision we had that lifesaver called as coefficient of restitution, sir, or elasticity. So do we have something like that here also?
No, you don't have anything here. I mean,
So we had to.
it won't get that big, but it's not that easy either. So brace yourself and try to do this question. That's all. When you come across this problem, try to do it. That's all. I can't really do anything else with it. Okay.
Okay, sir.
So that's it, guys. That's it for today. I've almost taken a class for 1 hour. So let's end it for today. And you complete, you practice, you keep practicing whatever you're practicing. In tomorrow's class, we will discuss more about gravitation. All right. Thanks so much, and bye bye.